Okay, next question. Very simple, conceptualized. Okay, so or conceptually. So what we have here is we have a signal where we have a Fourier transform such that the output is 0 for anything larger than some maximum component. So you can think of this as a baseband signal. Okay, so what this physically means is that you have a signal where it may look something like this, all right, and something like that, and then it's between f max, and then anything larger than that is equal to 0. So that's what we mean by baseband signal. So what they want you to do is, given these representations of that signal, what you would need to do is you have to figure out what the Nyquist frequency, what the bandwidth is in terms of f of max. So we're going to tackle each of these questions one at a time. So A. All right, so we have this in time domain. So what happens when we take the frequency, when we take a look at this in terms of frequency domain? Well, when you want to find, let's call it, okay, you know, let's take a look at, let's call it y. So if you find the Fourier transform, it's just by itself. And remember, this is the time shifting property. So this is x of f, and then e to the minus j 2 pi f, right? And then t naught is equal to 1. Okay? So if you see here that there's a common factor of xf. So if I factor out this, right, I get 1 plus e to the minus j 2 pi f. Okay? So notice that when you do a time shift, you'll see that here's the magnitude, but then it's scaled by a certain amount. So what's happening here is that the frequency components are not being varied at all. All you're doing is you're just changing the amplitude of each of the frequency components. So what does that mean? That means that the bandwidth is going to be the same. Because all you're doing is you're just changing the height of the actual frequencies, but the actual width, the actual spectral width, it should be exactly the same. Okay? So amplitudes change, but not spectral width. Okay? So therefore, the Nyquist frequency, which we'll call FNYQ, is just F max. Okay? That's it. Very, very, very simple. No questions there, right? Yes. Okay. The next one's going to be a little tricky. Okay, well, x squared is just x times itself, right? Yeah? So then what happens if I take the Fourier transform of this? Remember, do you remember that property where when you multiply in time, you do convolution in frequency? Yes. Right? So if I multiply two signals together, if I take the Fourier transform, I get 1 over 2 pi x of 1. Actually, it's not 1 over 2. We're doing it in terms of f, right? So it's just going to be x of 1, f convolved with x of 2. And do you remember what I talked about last class? When you convolve two signals together, the final width is just adding the two together, right? So if I'm convolving these two, if x has a bandwidth of f of max and x has a bandwidth of f max again, if I convolve them, I just have to add them together. So the output should be 2 times f max, right? Because I'm convolving it by itself. So if this has a width of f max, right, and this has a width of f max, if I do convolution, the output will be f max plus f max, which is twice as much. Okay? So this becomes, so x and then convolve, right? So a property is that given, let's see here, x of f, let's say x1 with bandwidth, let's call it a, okay? And given x2, well, let's say it has a bandwidth of b. If I convolve these two together, okay, the bandwidth is just the sum of the two. Okay, so therefore, the bandwidth of Nyquist frequency is just 2f max. Okay? So then if I were to do x cubed, that means it'll do 3 times. And then if I did x to the power 5, it'd be 5 times, right? So you're adding up as much as you have in terms of multiplication. Okay. Does that make sense? Good. All right, so the last one. It's a little tricky, but still doable. Okay. So remember, when you are dividing by a factor of, this is a factor of 1 over 3, this is what is known as an expansion. Okay? So this is an expansion, which means that you're going to take the time points and you're going to scale them by 3. But there's a property with the Fourier transform where if you took the Fourier transform of some time-scaled version, which will multiply by a, if you take the Fourier transform, this becomes 1 over absolute a x f over a. Okay? So this is the property. This is what's known as frequency scaling, I guess. All right. So in this case, my a is equal to 1 over 3. And then you can put the negative if you want. It doesn't really matter. But you can do x. This becomes 1 over 3t. And then if I take the Fourier transform, this becomes 1 over 3, which will be 3 in the end, then x f divided by 1 over 3. So in this case, this becomes 3x 3f. Okay? So what is this telling us? This is telling us that I'm going to take my Fourier transform and I have to shrink it down by a factor of 3. So what does that mean? That means my bandwidth is also going to shrink down by a factor of 3 because that's what the 3f is doing. I'm compressing the frequencies by a factor of 3. So the final answer would be f max divided by 3. Right? Okay? So therefore, the 3f does a compression okay? Therefore, the Nyquist frequency is simply f max divided by 3. Okay? Nothing to it. That's it. Okay? Very conceptual, no calculations. You just have to think about it a little bit. You have to know the Fourier transform properties if you want to answer this question. Okay? We're good? All right. Next one. Okay. We're starting to get a little harder now, and I'm going to do the hardest one at the very end. Okay, so I like to go from easy to hard, just to make sure that, just to whet your appetite a little bit. Okay, so let x of t be 2 sinc 2 pi t. So the first thing we have to do is figure out what the Fourier transform is. So before we get into that, let's review what the sinc function is. Okay, the sinc function is, it looks like a sinusoid that is decaying, that looks like a, it's kind of like a Gaussian, but it's kind of, it kind of converges over time. But then it crosses the horizontal axis at every multiple of pi. So in this case, it kind of looks like this, right? And then on the other side as well. Okay, so the height right at 0 is equal to 1, and then we have multiples of pi which intersect the horizontal axis every time. So this is 2 pi, this is 3 pi, and so on. It's obviously, it's not accurate, but I just wanted to give you a general gist of what the graph looks like. Okay, so sinc t. Okay, so how do I draw 2 sinc? Actually, I don't need to draw, but if you want, we can. So how would I draw 2 sinc 2 pi t? Okay, so what you have to do here is that remember that every multiple of n pi will give you zeros, right? So in this case, if I divide this, n is going to be equal to a half. So what this is saying here is that every time the axis hits a multiple of a half, it will go to 0. Okay, so in this case, the 2 sinc is going to look like this. So I have an amplitude of 2 here. It's going to go down like that. Okay. This is telling you what multiples of this factor will cross the x-axis. So we have a half. This is 1. This is 3 over 2. This is minus a half. This is minus 1, minus 3 over 2, and so on. So when you do this, what you're doing here is that every multiple of pi will make this function equal to 0. So all I do is I took 2 pi t. Right, so let me do this again one more time. So 2 pi t equals n pi. So I have to figure out what values of t will make this equal to 0. So when I solve for this, you get t is equal to a half n. Okay, so where n is equal to 1, 2, 3, and so on, or even negatives 2 if you wish. Okay, so this is saying that every multiple of a half, you will see that there are zeros on the sinc. All right, so let's just want to show you what that look like. So this is 2 sinc 2 pi t. This is just a bonus. You don't really have to know that, but I just wanted to show you what that looked like. Okay, A. Determine the determine the Fourier transform. Okay, that's not so bad. There is a property for that. So let's see. What do we got? Just double check. What question was this? This was 5. So 2. Okay, good. I have the property. I just don't want to go ahead. Okay, here we go. Okay, so there is a property. You'll get this. You'll get this for your midterm, but there is a property where you have 2b sinc and then 2 pi b of t. If you take the Fourier transform of this, this becomes rect f over 2b. Okay? So this is obviously, so my function originally was 2 sinc 2 pi t. Okay? So what does this mean? If you compare this with this, it looks like b is equal to 1, right? Right? So b is equal to 1. Therefore, the transfer function is simply rect f over 2. Okay, that's great. Okay? So this means that in the frequency domain, it's bounded between -1 and 1. So this would be the Fourier transform of this signal. And it's bounded between 1 and 1, and this amplitude is equal to 1. Okay, that's totally fine. All right? Okay, cool. So that's part A. Very simple. Now part B is to sketch the magnitude and phase of the following composite signal. So what this means here, okay, B, so we'll have y of 1 is equal to x of 2 times 0.5. Okay, so the order of operations on how you do this, you always do the compression first. So this, what this does is that it compresses by 2, and then you shift to the right by a half to the right. Okay, so we need to figure that out. So if you take a look here, there are 2 properties that we have to exploit. The first property is that frequency scaling stuff that I talked about earlier, and the second one is the phase shift, okay? So the first property we have to look at is this one here. Fourier, so 1 over a, and then x of f over a, right? That's the first property. The second property is the time shifting. So if I shift by a certain delay, the output will simply be the Fourier transform and then shifted over by some delay, which is, j, e to the minus j2 pi f t naught. Okay, so I need to combine these together to get my final Fourier transform. So I compress first, then I shift in the end. So the Fourier transform for this, okay, in this case here, my A is going to be equal to 2. No, sorry, yeah, it'll be equal to 2, right? And my delay is going to be equal to 0.5, all right? So I do the first one, so we have 1 over 2 x of f divided by 2, and then e to the minus j 2 pi f 0.5. So 2 times 0.5 is obviously 1, right? So this becomes a half x f over 2 e to the minus j pi f. Okay. And I also like to take a note that this is the actual spectrum, right? So before I get into this, this is what the original spectrum looked like. So if you want to take a look at it in terms of the magnitude, it's exactly the same, right? -1 to 1, and this is 1. In terms of the phase, there's actually no phase at all because everything is real. So because everything is real, there is actually no phase. No phase at all, okay? So 0 phase. So this is the original signal. Now what I need to do is I have to sketch this guy here. So what I need to do here is, what you can do is you can break this up into magnitude and phase, right? So if you remember, a signal can be decomposed in terms of its magnitude, right, and its phase. Okay? So if you compare notes, we have 1/2 x f over 2, right, and then e to the j minus pi f. So let's compare notes here. So this guy here is going to be the magnitude if you share them between them both, and then this here is going to be the phase. Okay? So the magnitude is basically going to look like this. So what's happening here is that we're going to expand the rect by a factor of 2, right? Because dividing by 2 means you're expanding. And then we also scale the amplitudes by a half. So this becomes -2 to 2, and then this is a half, like that, okay? Very nice. And now what's happening here is the phase becomes linear. So what this means is that it is a slope of minus pi. You have the minus here, so it's minus pi, and there's a slope of minus pi. So which means that from 1, we go down by minus pi, and -1, we go up by pi, and it just goes like that. So, okay? There. So this would be the phase. Okay? That's it. All right? Good? Okay. Let's do the next one. It's a little more complicated, but still very doable. The next one is this guy. So it's going to be the same, but there's a cos 10 pi t there. It's gonna screw things up a little bit. Okay, so next one. So the next one was, what was it, y of 2 equals, what was it? It was x of 2t minus 0.5 and then cos 10 pi t. Okay, we did this already. This is already done, all right? But now we have an additional cosine term. So we have to use an additional property. We have to use what's known as the modulation property, all right? So if you remember from last class, if we took some signal and we multiplied it by a cosine with a predetermined frequency, which we'll call f naught, if you took the Fourier transform, what you're doing here is that you're taking the original spectrum that's defined by x, and then you're making two copies of it. One defined at plus f0, and another defined at minus, and they're also scaled by a half. So when you take the Fourier transform, this becomes f of x f0, okay, and then plus half x of f plus f0. Okay, so you're making two copies of themselves. Okay, so all you have to do is take the spectrum that we found from the previous version, right? So x of t that. So what we did here is we took this. So all you have to do is just take the spectrum that we had here, and then you're going to make two more copies, and then scale it by half. So you're going to take this guy here, this rect, you're going to move it to the right by f of 0. So if 2 pi f of 0 equals 10 pi t, right? We need to figure out what f0 is, so f0 is equal to 5. So the frequency that this here is 5, so that you get 10 pi. So the frequency is 5. So what we need to do is we have to take each of these, move one to the right by 5, move one to the left by 5, and then we also have to scale each of these by a half. So you're going to get two rects that are 1 over 4 plus minus 5 hertz, okay? So therefore the magnitude is going to look like this. So we have minus 5, and then they're defined plus minus 2, so it's going to look like this. So minus 7, minus 3, this is scaled by 1/4, okay? And then 3, and then 7, scaled by 1/4 again. Okay? Remember, you're scaling by a half because you have these factors of a halves, and it was already scaled by half originally from this, from this over here. So you have a half times a half, which is 1/4, and that's what we have here. For the phase, it's very simple. All you're doing is you're just taking this line and you're shifting it to the right by 5 and shifting it to the left by 5, and that's it, right? So let me just do that on the next page. So the phase. So it's going to look like this. So 5, and then, okay? Something like, it will look something like that, okay? So we have pi, and this is 4, this is 6, this is minus 6, minus 4, this is minus pi. So it'll look something like that. I'm trying to put a negative, it just adds more. So, okay, and pi here, okay, and, sorry, whoopsie. It's all right, no problem. Sorry, whatever. Ugh. Sorry, it's bad palm rejection, this thing. It's okay. So 4, and then I guess let's make this more this way. Okay, like that. All right, something like that. All right, doesn't have to be exact, but that's okay. So you have two copies of themselves, one to the right and one to the left, and that's it. Okay, so the modulation kind of screws things a little bit, but all you're doing is you're making two copies of each spectrum. One that's going to the right, this is defined as f naught here, and minus f naught, and one to the left. So minus f naught and f naught. Okay, that's it. Any questions here? Okay, I've got a couple more, and then I'll let you guys go. All right. I'll try to end early every time. Okay. Yeah. Sure. Okay. Okay. This is question 6. All right. So a little longer this time, but completely doable. All right. Sorry? Oh, sorry. Okay. We've got two signals, G1 and G2, and they are transmitted through channels that are defined by the following two impulse responses. So H of 1 here is simply a it's a rectangular pulse function, and h of 2 is the same thing. It's another rectangular pulse function, but it's twice the width as the first one. Okay, the first signal is simply a rect function in time domain. Okay, so in this case, it simply looks like this. So we have 10 over 4, and then it spans like this, and then 10 over 4 divided by 2 is the spanning of that, which is going to be 50, it's like going to be 5,000, right? 10 over 4 divided by 2 is 5,000. Okay, T, that's the rect. And this one is going to be an impulse train with a period of 50 microseconds, right? Or 5 times 10 to the minus 5. So in this case, this guy here is going to be an impulse train that looks like this, where the separation between each impulse is defined by a multiple of the frequency, but the period, which is 5 times 10 to the minus 5. Okay. All right. So what they ask us to do here is they want us to figure out what the signals look like at each intermediate point. And then we also have a channel here that has a transform that looks like that. And then note that these are scaled by 10 to the power 4. So this would be 20,000. This would be 20,000 pi and 40,000 pi and so on. So we need to sketch the spectrum at each intermediate point. Okay, so what we're going to do is compute G1 and G2. So okay, that's fine. So we know G1, okay, is equal to what? It's not G1. Okay, let's do G1t first. So G1t is equal to 10 to the 4 rect 10 to the 4. Okay? All right. So now that we have this, let's just see where my solutions are. I just want to double check what we got. Yeah. Okay. Yes. Someone had a question? 10 to the power 4 is 10,000, right? No. No. No, it's 10,000. 10 to the power 3 is 1,000. 10 to the power 4 is 10,000. Divided by 2 is 5. Right? No, don't worry. I screw it up all the time. Don't worry about it. Yeah. Don't worry about it. Don't worry. It happens to all of us. Don't worry. Okay. So what we're going to do here is I'm going to make this so that we're going to divide by 10 to the minus 4. Okay. The reason why I'm doing this is because we have that special transform that we had, right? So if you remember, rect of t over tau, the transform was tau sinc omega tau over 2. Okay, so this is another property that you should know. Okay, so in this case, my tau here, right? It's not tau. Sorry, not tau over 2. So tau sinc omega tau over 2. Let me just double check. Oh, where is it? Oh, here we go. Sorry. Yes, tau sinc omega tau over 2. Yeah. Okay. Good. All right. Sorry, that's not it. Okay, so this is my tau here. Right? So in this case, tau is equal to 10 to the minus 4. So if I decide to take the transform of this, okay, this becomes 10 to the minus 4. Then there's also 10 to the minus 4 here that you have to copy over its constant. And then sinc omega 10 to the minus 4 divided by 2. Okay? So these two cancel, and then 10 to the minus 4 can be brought down here. If I multiply this by 2, I get sinc omega divided by 20,000. Okay, so this can be brought down to here, which becomes 10 to the power 4, and you can make that become 20,000. So that's the first one. Okay, so if you want to sketch this, it's very simple. All you have to do is make sure, all you have to do is make sure that, you have to make sure that this, every multiple of n pi will set this equal to 0. So omega divided by 20,000 is equal to n pi, which means that, let's see here, 20,000 n pi. So this means that at every multiple of 20,000 pi, you'll see zeros on the sinc. So in this case, it'll look something like this, right? So this is 20,000 pi, this is minus 20,000 pi, this is minus 40,000 pi, and this is 40,000 pi, and so on. Okay? and this is omega. So that would be g of 1. Okay, that's fine. Now we got to do g of 2. So g of 2 is an impulse train, right? So g of 2 is summation delta T naught. And T naught is equal to 5 times 10 to the minus 5. Okay? So if you remember the Fourier transform of this, if you take the Fourier transform of an impulse train, you also get another impulse train in the Fourier domain. We covered that last class. So if you want to figure out what the Fourier transform of this is, it's simply 2 pi. Right, I'm pretty sure it's the one. Let me just double check. Yes, 2 pi over T naught summation delta, and this is omega minus n 2 pi over T naught. Okay, and obviously this is omega, right? So omega is equal to, if you want to represent it that way, it's totally fine. Okay, so we have this. So this means that 2 pi divided by T naught is 2 pi divided by 5 times 10 to the minus 5, which is equal to, I guess, 40,000 pi. Right? So, yes, 40,000 pi. So that should be, yep, that should be fine. Good. Should be 40,000 pi if I recall correctly. Okay, good. So therefore, not change. I'm going to leave that out for now. So this becomes 40,000 pi okay, so that's the transform of that. So this is saying that we have an impulse train in the frequency domain which are separated by multiples of 40,000 pi. Okay? So multiples of 40,000 pi, it's going to look like this. So 40,000 pi, 80,000 pi, okay, and so on. So, okay, so this becomes g of 2 omega, and then this is 40,000 pi. Okay. All right, so that'll be G1 and G2, all right? So the next one, let's see here. We have to compute Y1 and Y2. So that's putting it through each of these filters. So we have a rectangular pulse with a 40,000 pi bandwidth and an 80,000 pi bandwidth as well. So B, the rect of, okay, it's simply this, right, with the value of 1. Okay, and then we have this one as well. Okay, all right. Okay, so that's what we have, all right? So now that we have this, what we have to do is we have to take each of our signals and put it through a filter. So this is essentially a low-pass filter. So any spectrum that is, in between 0 and 20,000 pi, you keep, and then anything bigger you set equal to 0. So if you remember what the sinc function looked like, you saw that it was bounded between multiples of 20,000 pi. So if I applied the low-pass filter, it's only going to capture this part of the signal, and everything else goes to 0 because the width is 40,000 pi, right? So the output for the first one is very simply just a hump like that. It only captures the main lobe. Okay? The next one, well, it's a little ambiguous because you have an impulse train that's defined here. So by convention, what you usually do is even though you filter it, so minus 40,000 pi is the largest signal or the largest frequency component you keep. So in this case, what you're doing is you're only keeping the first 2 impulses, which is, actually no, you have one of them as well over here. I forgot to define that one here too. So the impulse train is also defined at 0. So if you put a low pass filter here, you're just getting this part. Okay? So what you're doing there is you're just doing this. So you have 1, 2, 3. Okay? And that would be it for that. Okay. So now that we have this, all we're doing now is we're going to add them up and then put it through this filter here. So this filter is saying that at minus 4 pi, right, let's see here, it would go to 0, and then you scale everything up, and then you keep the 20,000 pi here. So actually, it's a little bit of a trick question. All you're doing really here is you're actually keeping everything, so it doesn't really make sense to do that. So if you put it, so all you're doing is you're adding everything up, and then you just filter using this, but notice that this, the largest non-zero component is 40,000 pi, so you actually keep that. So putting this through is actually a trick question. So if you want to figure out what the final output is, you just have to add them all up, right? So y1 plus y2, and then when you put it through the filter, it doesn't actually really do anything. So you have this, right? So this is 40,000 pi. Okay, and then what was the height of the sink? Or was it equal to 1? Yeah, 1. Wow, it's going to be really small then. Like that. Not that, sorry. So, right? So this is 1. Obviously not to scale, but that's okay. Okay. And then like that. Okay, so let me just make a note here. So putting through f of omega doesn't do anything. Yes. Again, making sure you're paying attention. All right? All right. Okay. Actually, you know what? I'm sorry. Actually, it does. I'm sorry. You know what? I stand corrected. If you take a look here, actually, no, we'll leave it like that. That's fine. Actually, well, the gain is very close to 0. So actually, what should happen, I'm sorry, is you should actually remove those. So in comparison to having a low-pass filter like this, where the gain is equal to 1, right? This case, there's a gain that's equal to 0. So what's actually happening is that you actually remove those. I'm very sorry. So what you have to do here is you actually remove these. Okay, so let me get rid of this. Sorry about that. So what's happening here is and then the filter removes plus minus 40,000 pi impulses. Okay? All right. Okay, let me just double check how much more I have, and I think I might let you go. Okay. I've got one for distortionless transmission, and then that's it. I'd like to do one question with distortionless, and we're good. So this will only take about a few minutes, and then I'll let you guys go. Okay, this is my last question for you guys today. Okay? I'd like to cover something with distortionless transmission. So, actually, you know what? I'll save that for next class. Forget that. Let's do that for next time. Let's do that for next time. Forget it. We'll do that for the next set of tutorial questions, all right? So, you know what? I think, let me just see what the last question is. So, 8, 9... sketch the spectrum. Maybe. You know what? This might be related to your... Okay, let me do this one. This is related to your pre-lab, right? This is the last question I have. This is the last question I have. Okay? Sorry, I want to make sure that you guys have enough to actually do the pre-lab, okay? Okay. So, okay, so what we have here is we have a... Okay, sorry, that's not it. Let me just... I forgot the first part of the question. Let me just do this last one quick. I think stay for a little bit because this actually is related to your pre-lab. I think this would be prudent for you to stay. Okay, this is my last question. So we have a signal, and then we also have a pulse train. So what we're doing here is we're actually sampling the signal, so with a periodic pulse train. So we're taking the signal and we're multiplying by a pulse train, and the signal is actually this thing here. It's sync. Okay. So we're going to do this question very quickly. I know you guys want to go. So here's the first part. So determine and sketch the frequency spectrum of this guy. Okay, so A. Okay, so what do I have here? So we have y of t is equal to 1 over 2 pi, and then sync squared. Don't worry, this will take me a few minutes and then you guys can go. I want to do this because it's related to your pre-lab and I want to make sure you have enough to do the pre-lab, all right? So there's a property where we have, let me see here. It was, there's a Fourier transform property where if you take b sync squared pi bt, the Fourier transform is triangular function. Okay? So in this case here, we can clearly see that b is going to be equal to 1 over 2 pi. Okay? So therefore, 1 over 2 pi makes sense because if you put b1 over 2 pi, it cancels out there, so you get 1 over 2t, so our t over 2. So this becomes delta f over, and then 1 over 2 pi, this becomes 1 over pi here, right? If you substitute 1 over 2 pi, it cancels, you get 1 over pi. So this means that the triangular function looks like this, okay? So it looks like a triangular function with a slope of, well, not with a slope of 1, but there's a height of 1 here, and this is minus 1 over 2 pi and 1 over 2 pi, okay? All right, so that's the first question. The second question is determine the Nyquist frequency, or in this case, the bandwidth. The bandwidth is very simply here, between here and here. So this bandwidth is equal to 1 over 2 pi. Okay? Next question. Okay. So remember, when you sample by periodic pulse train, what's going to happen is that the Fourier transform will copy the spectrum over that's defined by the sampling frequency. So if you want to figure out what the spectrum is for this, it's simply 1 over Ts, summation from minus infinity to infinity, of x of f n fs, where fs is equal to 1 over t of s. Okay? T of s in our case was pi over 2. That was given by the question. So the frequency, the fundamental frequency is 2 over pi. So this becomes 2 over pi, summation from minus infinity to infinity, x, f, n, and then this is n over 2 pi. Okay? So what this means is that you are going to copy the spectrum over by multiples of 2 pi. So the height becomes 2 pi. Okay, this is minus 1 over, so not minus, this becomes positive 1 over 2 pi. Minus 1 over 2 pi. Okay? And then I'm going to copy 1 over. This is 2 over pi. Okay? And this is 2 over pi minus 1 over 2 pi. And then 2 over pi plus 1 over 2 pi. And then you do the same thing over here. Okay, this is minus 2 over pi, and this is minus over 2 pi plus 1 over, oh sorry, minus 2 over pi and then plus. Okay, so that's what the spectrum looks like. Okay? And then the last question is very simple. What they want you to do is they want you to, so we have some filter h of f, and what they want you to do is they want you to figure out the right filter so that you get the original spectrum back, which is basically this. So what they want you to do here is they want you to find the range and then the value that you need to get the original filter back. Okay? So in this case, you want to put this spectrum, you want to put this through a filter. Okay? Such that you get the original spectrum back. Well, that's very simple. All you have to do is define a low-pass filter that is bounded between here and here. Okay? So the range that you want to filter, okay, is between, this guy here, this is actually equal to, this would be, let's see, minus 2, and then this is minus 3 over 2 pi, and here is 3 over 2 pi. So the range to filter is going to be between here and here. Okay, so the range to filter is between minus 3 over 2 pi to 3 over 2 pi. Okay, and then what you need is you have to make sure that so that the amplitude goes back to what it originally was. Okay, so in this case, all you have to do is just you have to multiply by pi over 2 to get the original scale back. Okay, so then therefore multiply or gain is low pass filter, yeah, pi over 2 to remove 2 over pi gain. Oh, because what you want to do is you want to define a low pass filter between here and here, right? Oh, they said the question is what is the maximum range you can specify, the allowable range. That's the, so obviously, you know, you can put it between here and here, no problem, right? But the question asks you, determine the filter gain and the allowable range. So the largest you can choose is between plus and minus 3 over 2 pi. Okay, so that is the largest you can choose between here and here. If you go anything more, then you're going to alias, you're going to capture this component. But yes, you would theoretically filter between here and here. That is what you would use. But the largest you can use is actually right here, between minus 3 over 2 pi and 3 over 2 pi. So that's before touching the other lobes. Okay, and that's it. So you would use 2 over pi gain to get back the original signal. Okay, that's it, guys. I'm done. So next week, actually no, next Monday we've got a holiday, so I'm not going to see you until next Wednesday. Next Wednesday we're going to start covering more more, more material that's relevant to the course. So we're going to start amplitude modulation next week, which is a really exciting topic. Okay? See you guys next week.